Hello everyone. I wanted to provide you all with an extra review for standard deviation. Having gone through the discussion board post for last week for week 4 in regards to standard deviation and variance, I noticed that there were a lot of issues that many of you were having in terms of confusion associated with standard deviation. I wanted to make sure to take the time and really help you all really try to understand the information associated with standard deviation, also when to try to apply the use of standard deviation, and distinguishing between the population versus the sample standard deviation and variances. I know that in the textbook it seems a tad bit confusing looking at this differentiation between population versus sample, and that is a distinction that we need to really make all semester long in terms of when it is that we're talking about a sample versus when it is that we're talking about a population. As I mentioned in my lecture for this week, for week 5 for frequency distributions, I mentioned that 99% of the time I'll be talking about the sample versus the population because the sample is really what we as researchers in psychology are going to be working with. Very rarely, if ever, will we really have the population available to us to be able to do something associated with the population. Rather, we use the sample to then make inferences about the population. So even though we really won't be talking about the population very frequently, it's still important for us to make that connection between the two. That whatever data it is that I calculate for my sample, I'm thus then going to conclude that about my population. So just as we did with our measures of central tendency, in that we said, well, what happens in the case where x bar equals a value of 80? What would mu be equal to? Mu would also be somewhere around an 80. Why? Because again, remember that my stat is a point estimate representation of my population parameter. So in the case for standard deviation, I would assume then that whatever the standard deviation value would be, so let's say S for standard deviation, because that is the symbol that we use for standard deviation, we use S. Sometimes you'll see me say SD, just because I like to make that distinction that we're talking about standard deviation. So let's say the standard deviation is a 2.42. What would then my population standard deviation be equal to? My population standard deviation would then be equal to somewhere around the same value, to a 2.42, or I would assume that. So in terms of the sample versus the population, whatever data it is that we collect and we calculate for our sample, we're always then going to assume that it's going to be a point estimate representation for my population parameter in every single case. So there's not going to be a case where you're ever going to say, well, I calculated the group's performance and the group's performance was an 80, but in the population, I'm thus making a prediction that the value for my population parameter is going to be a 20. Well, why would we ever want to do that? I mean, that was the point of us getting people from the population to represent them, right, as our sample from the population to then be able to calculate whatever value it is that we want and thus then make an inference about the population. So the same thing happens here with standard deviation. Whatever value it is that we calculate using my sample, so again, individuals who are supposed to represent the population, I'm going to assume then that the population parameter would be identical to that. Now, do just realize that there is a difference in the way that we actually calculate standard deviation for the sample versus the population, and that's what I want to talk about in this couple of minutes here. So when you look at the formula for standard deviation is calculated as the following. We're going to have the sum of our squared deviations, and we're going to divide by n minus 1, and we're going to take the square root of that. Right? That's standard deviation. Now, for variance, which is s squared, right, or I'll label it as variance, we're going to have the same formula, so the sum of our square deviations divided by n minus 1. But now you'll notice there is no square root. That's the only difference between standard deviation and variance, to be honest with you. Now, both of these here are for my sample. Now, how do I know that they're both for my sample? Well, they're both representing my sample because, again, I'm using lowercase n. Remember that lowercase n always refers to my sample, while capital N refers to my population. So again, lowercase n refers to the sample size, right, associated with my sample of individuals. Capital N refers to the population size. So here I know that I'm working with a sample because I'm using lowercase n. Now for the population here, the formula changes just a little bit, but the population standard deviation, and here in our particular case, it's going to be this particular symbol here, and it looks like an O, but it's just kind of like a fancy O that we have here. It's going to be the exact same formula, so the sum of our square deviations divided now by capital N. And here we're going to take the square root of that, okay? Because again, here we're talking about standard deviation. Now, in the case where we're going to be dealing with the population variance, so in the case for our population variance, our formula is going to look exactly like the way our variance formula looks like from our sample, but now just again just a little bit different in this particular case. So our population variance, or what we call sigma squared. So this is sigma squared. It's going to be the exact same formula. So sum of my squared deviations divided by capital N, but now you'll notice there's no square root associated with that particular formula. And again, the reason, because it wants to actually interpret our results using squared scores. So the difference between, again, standard deviation and variance for both the sample and also for the population is that standard deviation uses the square root sign while variance does not use the square root sign. So you'll notice that in both of these cases, so again, remember this is for my population, both standard deviation uses the square root while variance does not use the square root. So again, variance likes to interpret our data based on squared scores. But then again, you didn't give me squared scores. So let's say that you have a scale that goes from 1 to 9, and you gave me a value of a 3. You didn't show up to my study and tell me, well, I went ahead and gave you a value of a 9 because I know you were going to square my score when looking at standard deviation. No participant thinks that way, but rather what we do, all that we say is, well, I'm just going to be dealing here with the score that an individual gave me. So thus why I need to take the square root to eliminate the squaring that I actually did when I was calculating my sum of squares. So remember that the top portion of my formula here, and let me go ahead and just get a clean sheet there for you. The top portion of my formula, so the sum of, oops, I made a mistake there. So it is the sum of my square deviations. So again, remember that in certain instances what you're going to see is they're going to tell you that S, or standard deviation, equals sum of square divided by degrees of freedom. You're going to take the square root of that. Sum of squares is equal to this. So this is actually sum of squares. So whenever it is that you see this formula here and they say calculate sum of squares, they're essentially saying do this. So let's say, for instance, we're doing the following data set. So here's my data set. Value of a 2, 3, 4, 5, and 5. So we're going to go ahead and work through this example if you all would like to follow along. So in our particular case here, the first thing that we need to do is we need to know what sample size is. Why do I need to know what sample size is? Because to calculate my average, I still need to know what my sample size is. Right? So that would be the first step. So here I have 2, 4, 5 values. So in my formula for my mean, I know that my denominator is going to be equal to 5 because sample size is equal to 5. Now we're going to do the sum of x. In this particular case, it's 5 plus 4 is 9, plus 5 should be 13, plus 5 should be a value of 18 if I'm not mistaken. So again, 10, 14, 17, 18, 19, sorry, it should be a value of a 19. So that should be 10 plus 4 should be 14, plus 3 should be 17, plus 2 should be a value of a 19. So it should be 19 divided by 5. So here, if you do your math, so again, go ahead and calculate 19 divided by 5. And that will give you a value equal to 3.8 as my mean. Okay, so that's your average, a 3.8. So if we look here on our formula, the next step in our formula tells us, okay, you're going to take each score and you're going to subtract the mean from it. So here, my scores again are 2, 3, 4, 5, and 5. Now I'm going to go ahead and take the mean from each one of those values. I'm going to subtract the mean. Now here, remember, you're going to get some positive, some negative values, and that's okay. Don't worry about that. That's where the whole squaring part is going to come into play. So here, 2 minus 3.8 should give you a value of negative 1.8. 2 minus 3.8 should give you a value, 3 minus 3.8, here we go, is minus 0.8. 4 minus 3.8 is a value of 0.2. 5 minus 3.8 is a value of 1.1. So remember, these are positives. We're going to get the same value here for our last one, 5 minus 3.8. Now remember here, we don't want to go ahead and sum up our scores, because if we sum up our scores in this particular case, we're going to go ahead and get a 0 value here, and we want to make sure that we avoid that in this particular case. Okay, so again, remember, we are going to go ahead and square all our values. So here in our particular case, what are we going to do? We're going to go ahead and square. And again, if you just would like to confirm that this would equal up to a 0, you can definitely do that. So 1.8 plus, so negative 1.8 plus negative 0.8 should be equal to negative 2.6. So negative 2.6 plus 0.2 should be 0.4, 2.4. So plus 1.2 positive should now be equal to 1.2 plus 1.2, again, should now give us a value of a 0. So here we want to make sure that we avoid that. So what are we going to do? In our particular case, we're going to go ahead and square all our values here, so that way we can get rid of our negatives in our particular case. So you're going to go ahead and square. So 1.8 squared, and here, if you do have your calculators available, go ahead and use them. So 1.8 squared should be equal to a 3.24. Now remember here that even if you have a negative or a positive, whenever you square a value, that negative will automatically become a positive. So negative 1.8 becomes positive 3.24. Negative 0.8 squared is going to give you a value of 0.64 positive. 0.2 squared is going to give you a value of 0.04 positive. 1.2 squared is going to give you a value of 1.44 positive, and the same is going to be for the last value here, since they're both equal to a value of a 5. Okay, now here, after we've actually done the squaring, right, so again, remember, following order of operations, you plug in your score minus your average to give us our deviations, because remember, this portion here, this is what's called the deviation, okay? And that's a very important term that we have to all familiarize ourselves with in terms of standard deviation. Thus why we call it standard deviation, because we are literally calculating the standardization of deviation from the scores to the mean, right? So in other words, trying to calculate an average. So now once it is that we have our deviation, which are all these values here, we're going to square them. So now when we sum up our square deviation, so here in our particular case, we're going to go ahead and do that. So if you have your calculators again handy, 3.24 plus 0.64 plus 0.04 plus 1.44 plus 1.44 should be equal to a sum of 6.8. Okay, so my numerator here in my formula, my sum of squares, and again, remember, I've told you, I really don't like that term sum of squares. I really like the sum of square deviations, because that's really what these are. These are the sum of the square deviations is equal here to a 6.8. So again, remember, our sum of our square deviations in our particular case here is equal to a value of a 6.8. And now we're going to divide by our degrees of freedom. Remember that degrees of freedom equals n minus 1. So n minus 1 equals degrees of freedom, because remember, we're talking about sample standard deviation. So in our particular case here, all that we're going to do is we're going to have our sample size, which is equal to 5, and we're going to subtract 1, so that should be equal to a value of a 4. So 6.8 divided by 4 should give you a value of a 1.7. So if we calculate this, so 6.8 divided by 4 equals 1.7. If we were to stop right here, this is equal to variance for my sample. Okay, so it would be equal to s squared, okay? But here, I'm not interested in the sample variance because, again, remember, I don't want to deal with squared values. So that's why I don't use variance very frequently in terms of my statistical discussions, because I'm not working with squared values. I'm working with the values that were actually in my own format. I wasn't working with squared values because I had to square them here to get rid of the negatives. So here, I'm going to go ahead and take the square root of 1.7, and the square root of 1.7 in our particular case should be equal to a value of 1.30. So 1.30 is standard deviation in our particular example here. So you're probably saying to yourself, great, so what does that mean for me? What does it mean to actually have a value of a 1.30 for standard deviation? So remember here, what's the purpose of standard deviation? Think of the definition for standard deviation. The definition for standard deviation is, on average, how far do my scores deviate from the mean? Because remember, I'm using the mean here as my central point to see the distance between my scores to my mean. Why don't I use the mode? Why don't I use the median? Well, because those aren't very stable values from sample to sample. The mean is a stable sample, a stable value from sample to sample, and it also takes everyone's score into representation. So here, it's actually an ideal value for us to be able to use as a central point of contact to see how far everyone deviates from that central point. That would be an ideal situation. Now, in this particular case, let's say that we have a 1.30. So what does that mean? Essentially, we're saying, on average, every single score in my data set is about 1.30 values away from the mean of 3.8. Now you'll notice and you'll say, well, 2 is not exactly 1.30 values away from the mean. It was 1.8 values below the mean. So why is standard deviation then not a value of a 1.8? Because again, remember, it's an average. Again, it takes everyone's score into consideration. So here, since it's taking everyone's score into consideration, some scores are higher, some scores are lower, thus potentially then giving us a value that may not necessarily represent everyone's distance from the mean, but it shows us everyone's general distance from the mean, taking everyone else's distance from the mean into consideration. So here, think about that, right? That we're saying, well, how far are we on average? Because again, average is taking everyone's score into consideration from the mean, right? That's what a standard deviation of a 1.30 would be. So you're probably asking yourself, well, great. Okay, so now I know that it's a 1.30 and that I'm about 1.30 values away from the mean in terms of every one of my scores. What does that mean? Well, standard deviation here in this particular case is low. That's a good thing. We want low standard deviation. To be honest, we don't want high standard deviation. That's something we want to avoid. I don't want more standard deviation in reality. I want lower standard deviation, less variability in my scores. Why do I want less variabilities in my score? Because if I have less variability between my scores here, that means that everyone is reacting the exact same way in terms of my manipulation or my control. So let's say, for instance, that I now implement some manipulation. So let's say that I have an example like the following. I'm going to have online versus in-person classes. And what I want to do is I want to look at people's scores online. So online, everyone receives the exact same material in the exact same way every single time, and they're only allowed to view all the material one single time. Hopefully, what I am hoping for in a perfect world is I want everyone's scores to be equal. So let's say their scores can range between a 1 to a 10. So I want people's scores to all be the same. So here, everyone reacts exactly the exact same way. So again, everyone gets a value of a 5. That would be fantastic for me, because then here no one is deviating from the mean because my average is equal to a value of a 5 since everyone's score is equal to a 5. So I have a standard deviation equal to 0. I have variance equal to 0. This would be ideal. So this is an ideal situation, okay, that there's no variability, because then I would say my manipulation or control completely works because everyone is acting the exact same way. It's affecting everyone the exact same way. But that's not going to happen. So some people may get a value of a 5. Another person may get a value of a 3. Another person may get a value of a 4, a 6, a 7. and we'll leave them at those values. So here, since not everyone scores identical, thus they're all deviating from my average, right? Whatever my average is going to be. So my average, I calculate my average in my particular case, right? Whatever my average is going to be. Now I want to know about, on average, how far people are deviating from there. So now if I calculate standard deviation gives me that estimate, the estimated distance in terms of an average, for an average deviation. And that's what I want. It's an estimate of distance in terms of an average deviation. So in other words, on average, people are about 1.30 values away from the mean in our particular case, right? That's what it wants. So here also, standard deviation would be a very good measure of error variance. So in other words, remember my definition for error variance. I've talked about it 100 times by now. So is it going to be on your exam? Probably. So here in our particular case, error variance. What is it? Differences in our scores that are not due to the researcher's manipulation or control. In other words, how far people are deviating from each other in terms of an average. So in other words, if everyone is reacting the exact same way to the manipulation, everyone's score should be equal to each other, but they're not. So in other words, there's error that is occurring in here that is changing my scores that are not due to the researcher's manipulation or control. So in other words, let's say that person number 1, they studied and looked at all the material only one time. Person 2 looked at only half of the material. Person 3 looked at 95% of the material, etc., etc., etc. So thus the differences in my scores are not necessarily due to the online platform, but they're due to the online platform plus differences in terms of how much of the information that they actually viewed. Okay, so standard deviation gives me a measure of error variance. SD should be low. This would make me very excited if I had SD very, very low, as close to 0 as possible. Is it ever going to get close to 0? Yes. Is it going to be 0? No. Never will it be 0. If standard deviation is in some way equal to 0, everyone's eyes would open up and we would all question that right away. And why would we all question that? Because it's not feasible. It's not realistic for everyone to be affected in the exact same fashion. Differences have to exist because people are just naturally different. Thus, we're going to have those deviations occur. So here now, let's try out a couple of examples. And I just realized I spelled examples wrong, so please ignore my misspelling blunder in this particular case. Now that I've told you it, you're just looking at it, right? That you're just like, well, this is awkward. So there, let's try out some examples, right? I fixed the issue for us. So again, let's look at the value of a 2, 3, 4, 5, and 5. We already went through this example, so SD equaled 1.30, variance equaled 1.7. But now let's look, so again, remember this was for my sample. Now let's look at the population. So let's calculate the population standard deviation and the population variance using the exact same values, 2, 3, 4, 5, and 5. So we already know what our deviations were equal to in our previous case. And if I remember correctly, my sum of my square deviation should have been equal to a 6.8, right? Because then we divided by 4, and just to confirm, 6.8 divided by 4 should be equal to 1.7. So here, 6.8 was equal to my sum of squares. So nothing changes there, right? But now we don't want to use 4 because 4 was representative of the sample because it took n minus 1. So n equaled 5. We took minus 1 to get our degrees of freedom because the formula for standard deviation, again, was the sum of our square deviations divided by n minus 1. And we're going to take the square root of that. Here, for the population standard deviation, we are going to use the same formula. The only thing that changes now is the denominator. So it's going to be the sum of my square deviations divided by n. So in other words, all my scores. So rather than dividing 6.8 by 4, we're going to divide 6.8 by 5. So remember, 6.8 doesn't change because it's still going to be the exact same sum of square. So it's still going to be the same deviation. My average doesn't change. the deviations don't change, the square deviations don't change. So that's why I know it's equal to a 6.8 because it's from our previous example. And here again, you guys can work through the math and get that exact same value. So it's 6.8 divided by, not degrees of freedom, right? We're going to divide by capital N. So in our particular case, 6.8 divided by 5 gives me a value of a 1.38. So now variance, because again, remember we use the symbol of sigma. Here, if you just say variance population, I'll be okay with that too. So if you don't remember the sigma symbol or the name of this symbol, don't worry about it. As long as you say the population variance, I'll be fine with. That's going to be equal to a 1.38. Again, remember, I don't work well with squared values, so I need to take the square root of that. If I take the square root of 1.38, that should now leave me with a value of sigma, because remember, sigma here is representative of standard deviation for my population. And again, here you can say population standard deviation, and I'll be okay with that, is going to equal a 1.16. So in other words, on average, people in the population are deviating about a 1.16. So again, remember, these values here in this particular case, sigma and sigma squared, we would assume then to be accurate representations of the population parameter because these are population parameters. So whenever it is that we use these symbolic notations just as we have done here in terms of our Latin values, we are automatically going to assume that we're always talking about the population value. Now here, if you notice, standard deviation for our sample was a 1.3. Here, standard deviation for the population is a 1.16. So thus, they're very close to each other. They're not exceptionally or extremely different from each other, very, very close to each other in both cases. Thus, we can use this value here to be a good estimate. Now here you're wondering, well, why is this value a little bit higher than this value? Why isn't it a little bit closer? Because remember, our denominator here in our case is lower. A smaller denominator is essentially going to mean a larger overall value. Why is it going to be a larger overall value? Well, because remember in terms of math, 1 divided by 4, 1 divided by 3, 1 divided by 2, our value continued to grow, right? So 0.25, 0.33, and then 0.50. So we saw our values increasing as our denominator got smaller. So mathematically speaking, having a smaller denominator in our case gives us a larger standard deviation because we're conservative. So we are conservative in terms of our estimates. So here, what does it mean to be conservative in terms of your estimate? It means we're much more comfortable saying, hey, there's a little bit more error in my data set rather than there is less error. Because I may be wrong at less error, but at a higher error, if I still get this and I'm still okay with this amount of variability in my scores, I'll be okay overall. Okay, that's why we have that lower number in these particular cases. So let's go ahead and talk about our final issues for our discussion of standard deviation and variance. What I wanted to do is I wanted to talk about the both benefits and limitations associated with standard deviation and with variance and when it is that we would want to use both statistics. So first, let's begin with variance. Variance is a very easy one to think of in terms of when it is that we want to use variance. So when do we actually want to use variance? Very rarely, to be honest with you. Why is it that we would very rarely ever want to use variance? Because variance, again, remember, is a squared term. So here, variance is going to give us a squared response. So if we were ever to say, well, my variance associated with with the variability in my group was a 1.76, we're saying on average our squared scores deviated about 1.76 values away from my average. So here, how do you interpret a squared score? Because again, remember, your participant didn't give you squared values. Your participant gave you a value of a 2, not a value of a 4, right? Because the 4 would be a squared value associated with our 2. So if we square 2, it becomes a 4. But here, the participant didn't give you this. The participant gave you that response. So here, to be honest with you, variance, we're very rarely ever going to use variance, but variance is important for the calculation of other statistics that we're going to be talking about this semester. And I'll make note of them whenever it is that we approach those statistics and we discuss their relevance associated with our course. Now, what's the benefit then of calculating variance? The only real logical benefit that we have associated with variance is that it's used in the calculation of other statistics because they do require square deviations in those particular cases because the theorems associated with those statistics are going to require variance in those particular cases. But for our purposes here, we're not really going to worry so much about when it is that we would want to use variance. What's more important is for you to know what variance is. So again, remember, variance is, on average, how far our squared scores deviate from the mean. That's the key difference between standard deviation and variance. So standard deviation, not squared. Variance is a squared term. So here, all that we've done to variance is we've taken the square root of variance to come up with standard deviation in our particular case. Right? Now, what's then the benefit of using standard deviation? Standard deviation is a great estimate. So it's an estimate of error variance. And it's also a good estimate to tell me deviation. So it will tell average deviation. That's what it's going to do. So average deviation of our scores from the mean. Okay, so it's going to tell you the average deviation of scores from the mean. And here I probably shouldn't say x bar because that means our mathematical mean. So here the average deviation of scores from the mean. That's what the purpose is of standard deviation. So again, I want to know how far my participants are from each other in regards to the distance from the mean. So again, I have the values of a 2, 3, and a 4. I want to know how far it is that they actually are from the average. So again, here, my sum of x would be equal to 9 divided by 3 would be an average equal to 3. So I want to know on average how far everybody is from this mean of a 3. But I don't want to know individually how far participant 1 is, participant 2, or participant 3. What I want to know is I want to know as a group how far everyone on average is from the mean. Now, why is it then important to note outliers? Well, if we look at this particular situation here and we actually calculate our standard deviation, here we can just use this example very quickly. So 2 minus 3, 3 minus 3, and 4 minus 3. Here our deviations should be equal to -1, 0, and +1. If we square these values now, in this particular case, we're going to get +1, 0, and +1. So my sum of my square deviations, so sum of the squared deviations is going to equal, in this particular case, to a value of a 2. And then we're going to divide, in our case, because I'm talking about the sample standard deviation, so I need to do degrees of freedom, so n minus 1. So in our particular case, we're dealing with a value of a 2 as well. Because we have 3 values, minus 1 is going to be equal to 2. So 2 divided by 2 is going to be equal to a value of 1 in our particular case. So 2 divided by 2 is going to give us a value of a 1. So in other words, we're saying on average, every single score is deviating about 1 value from the mean. So in this particular case, that's actually quite correct for this value and for this value, but not for this value, because that person there actually scored the mean. So for them, standard deviation doesn't make any sense for them, but yet it's still a relevant statistic for us to actually use in this particular example. So here in this particular case, we have a standard deviation of 1. But now let's include an outlier. So 2, 3, and we're going to put a value of a 10. So here, my sum of x is going to be equal to 15 in this particular case. So 15 divided by 3, because I still have a sample size equal to 3, is going to give me a value of a 5 as my average. So 2 minus 5, 3 minus 5, and 5 minus 5. Now, why is it that my average goes up in this particular case? Because I have this outlier here. I have this value that's very extreme in comparison to my other values. In this example here, everyone's pretty close to each other. I mean, we're talking about a range of a 2, because we're talking about the highest value being equal to a 4, my lowest value being equal to a 2, I have a range of a 2. But now here my range is an 8. 10 minus 2 is going to be equal to 8 in our particular case, so my range is getting up there, right? So there's more spread in my scores. So here, this outlier is pulling my range to be higher, and it's also pulling my average in this particular case to be higher because it's such a large value. So here I've jumped from having a mean of a 3 to a mean of a 5, which is pretty substantial for 3 numbers. So here if we calculate our deviations, so here we're going to have minus 3, we're going to have minus 2, and plus 5 in this particular case. So now we're going to square all our values, again following the order of operations. So we're going to have a value equal to a 9, 4, and a 25. So here 25 plus 4 plus 9 is going to be equal to a sum of my squared deviations is going to be equal to a value of 38 divided, again, remember by my degrees of freedom, n minus 1 is still going to be equal to a value of 2. So here now it's 38 divided by 2 gives me a value of a 19, and we're going to take the square root of 19 is going to equal a value of 4.36. And here I just realized that I forgot to take the square root of 1, so this is actually variance in our previous example, but the square root of 1 still equals 1, so here we really shouldn't have a problem with that. So here my standard deviation is still equal to a 1 in that particular case, but now my standard deviation is equal to a 4.36 in this particular case. So I took the square root of 19 because 38 divided by 2 is going to be equal to a value of a 19. That's going to be variance in this particular case, right? So this is variance. 4.36 is now standard deviation in our particular case. So standard deviation now has jumped from being a 1 to being a 4.36. So here, that's very important for us to understand that. Why is this important for us to understand? Because look at what's happening to one extreme value in my data set. So two of the other values are exactly the same as they were in the previous example, but now one of our values has jumped from a 4 to a 10. Now it's pulling my standard deviation up as well. So just as the effect that outliers have on the mean, that it could potentially pull the mean up or it can pull the mean down depending on the direction, right, of the outlier. Here the same thing is happening. Having an outlier that is pulling the mean up is going to pull standard deviation up as well. So it's going to make standard deviation be larger because it's going to make it look now like if there is more spread in the scores, because technically there is. So two of my values are actually pretty close to the mean, but one of them is kind of far away from the mean. So it actually ends up pulling my standard deviation up higher. So here, rather than us saying, well, on average, there's about one value away, or sorry, on average, our scores deviate about one value away from our mean. Now we're saying on average, scores deviate about 4.36 values away from our mean. And again, remember that the term deviate essentially just means spread, so distance, right? That's essentially what we're talking about here. So we're saying in this particular example, there's more distance from our scores to the mean than there was here in this particular example because of the outlier. So that's why it's important to note those outliers, because outliers themselves are going to be dragging my my standard deviation in a general direction, either higher or lower, because they absolutely do have an effect. Because again, remember that standard deviation is an average, and the average is easily affected by outliers. Also, think of standard deviation doing the following. So let's say, for example, our values of 2, 3, and 4 that we were working with, right? So my values of 2, 3, and 4 had a mean equal to a value of a 3. So here, let me just change colors here. And what I'm going to do is I'm going to say that my value of a 3, so I'm going to say 1, 2, 3, 4, and 5. So my average was about here, right? We're going to say that my average was there. I'm just drawing this dot there, right? Because that's my average. But now the different colors here that I'm going to have are going to correspond to my actual values. So I have a value of a 2, and a value of a 4, and a value of a 3, right? So here, if we think about the distance between that value, the red value, and the mean, it's right on top of it. There's no distance, very little distance between those values there. But now let's draw a different distribution where we have our scores 2, 3, 4, 5, 6, 7, 8, 9, and 10. And now my average in this other particular example was a value of a 5. So here's my average in that particular case. And now I'm going to draw my values. Here I'll change to green. So I had a value of a 2, I had a value of a 3, and I had a value of a 10. So this value to that value, not too much distance, not too much distance, but here, look at all that distance that we're covering here. So essentially what's happening here is in this particular case, there's more spread in our scores because of this outlier. So that outlier is pulling my mean higher, making it look like if we had a lot more spread. Here, there's less spread because all my scores are very close to the mean here, which is that green dot right there. So all my values are a lot closer. Here, if you want, you can draw a circle over that so you can see how much spread there is between them, right? So you see that? So there's a lot more spread in this example than there is here. So that wraps up our discussion or our review associated with standard deviation. I hope that this has helped you try to understand a little bit better associated with standard deviation and why we use standard deviation and how we use standard deviation. I do strongly recommend looking through the video multiple times just so that way you can make sure that if you do have any questions to please let me know. Feel free to email me or ask me any questions, or if you would like to call, you can also absolutely do that.